Okay? Great. Let's get started with a recap. Okay? What's the main message yesterday? So, big picture message is, it's not physics drives the world. It's too big picture, a little bit less big picture than that. This is a bit too much. I'm gonna get there. But the main message would be, big picture message would be, space is important in biological processes. Then there is stochasticity, there is randomness changing in time. Okay? Therefore, diffusion is important. Randomness, like as in random walks. In the random walk, saw that the position thing obeys this. Very simple. Jumps right or to position in the old position. And then we saw that this is 0 for many particles, but this is not. And S, where T, number of steps, times duration of, and D, called is size of the step squared divided by 2 divided by the times the duration of this step. Okay, this is a random walk in discrete space. How about in continuous space? Continuous space, we saw that things change a little bit. Okay, because in continuous space, the duration of each step goes to 0. The size of the step in space goes to 0, and the duration of the step goes to 0. Approximately. And as a result, in a finite, small time step, but finite, not 0, a finite, small time step, there are millions and millions and millions of random walks, each of them with almost 0, actually. As a result, you do not get this. That is, the position of the particle is not only the previous position plus or minus a fixed size step. Instead, what you get is the combination of such guys, which leads to a Gaussian variable. Okay? So the increment coming from a Gaussian distribution because of the central law makes the sum of many of those guys become Gaussian variable that. Okay, so saw that this case new position equal to the old position where delta t finite all time step doesn't need to be small. Small, there are other forces. But if you have only these, then have the old position plus the random or the stochastic, in which we saw this. Where eta is the Gaussian variable which you draw from a Gaussian distribution at time t, draw an E1 and 1 at t, 2 delta t, and so on. Okay? And this variable, the Gaussian variable, has zero mean. You draw many of these variables into a plot. Distribution has a zero mean. And the correlation, I didn't say this explicitly yesterday, but the correlation I mentioned yesterday the correlation of variables that depended on time steps. I made it chi n with chi m. So here similar, but instead of a Kronecker delta nm, now you have a Dirac delta. This function is basically zero everywhere except when t is equal to prime, meaning that value of eta at t is completely independent, correlated to the value at t prime. Okay? This is something that you can use sometimes when you integrate things. Anyway, don't worry about these. And what was the name of this? This is the Euler-Maruyama method to simulate in discrete time Brownian particle. These actually for other stochastic differential equations. See that I just mentioned differential equations. So where, if I'm talking about differential equations, where is the derivative? Here is the derivative. So we could try to construct a derivative here. Get these. Okay. This would be like definition of a derivative if delta t goes to 0. Very small delta t. But then we have a problem because if we have square root delta t here, to divide by delta t, we're going to have 1 over square root delta t. When we make delta t very small, thing will diverge. We cannot actually define derivative as we do outside stochastic calculus. Topic called stochastic calculus. Different type of calculus of derivatives and integrals. But people still kind of write down things using the sign or the notation of derivatives. And we're going to write these here. This is how we are going to represent these. There is no delta t anymore. So the velocity, call it velocity, just said it's difficult to, but velocity of the particle, of the Brownian particle, is a number times a Gaussian. Okay, velocity of the particle is changing all times it will receive a kick to the left, right, changing all velocity. Positive. Okay. Okay. Can we write something similar to that, but starting from Newton's second law? Because this is kind of an equation of motion, right? How the particle moves. Usually what we do is we start from second law, force equal to mass times acceleration, and we get something out of that. Can we do so? Okay, so if we do something similar, so from Newton's second law, what we get actually is the following. So mass times acceleration. So acceleration is the derivative of, second derivative of position. Okay? Rate of change of the position. Velocity, the rate of change. Velocity is time. But then you get, so this is the net force, so which corresponds to a bunch of forces that are acting particle, which are, so what are the forces that your Brownian grain small particle? It will be receiving forces from the kicks of the water molecule. Okay? And how do we write these down? So imagine that you are a particle moving passively. You are just receiving kicks. When you end up moving in this direction, there is a sort of unbalance with respect to the heat that you receive here compared to the heat that you receive on your back, right? Because you are actively at that moment going in that direction. So there is kind of unbalance. So there's going to be a net force is contrary, the opposite direction with respect to your movement. This force is called drag force. So when you have an object moving air, you will feel a drag. Okay? So the average result of these heats of the water molecule, what we call the drag, the average. Okay? So you can write it like this. Is a force that is opposite to your current velocity. Your velocity is dot. Minus is the opposite. Right? And gamma, what's called drag constant. Okay? You have a ball of paper like this, the drag constant is different than an open paper. Okay? So this number depends on that. But this is the average effect of the water molecule heating object, there are fluctuations. The fluctuations are exactly this. Okay? So it's a Gaussian variable fluctuating from time to time. Particle. That's something like there is a gamma outside. Yes. Yeah. So the gamma outside. I'm going to all things become consistent. Okay. I needed to put this gamma outside here because what we had before was a velocity. Because this was a velocity. Okay? X dot, this is the same as X dot. Okay? So this was a velocity. But here I'm talking about forces. One force plus other force. So we need this gamma here. Take correct? Okay? But this doesn't matter. Imagine that this whole thing is just a number. It measures the intensity of your fluctuation. Okay? Because this number here, eta, Gaussian number, has standard deviation 1. So you control the intensity of the fluctuations with these other numbers multiplying it. Okay? Okay, but this is different. This is not the same as this. One equation, this is another equation. What's wrong? So basically what we're going to see is the following. I think it's going to become clear now. This guy is actually 0. Okay? This guy is 0. Everything is. Do you agree? Why this guy is 0? This guy is the acceleration mass, total force acting on your particle. This is 0 because we are working here. We're going to be working here in what's called the overdamped regime, which means that there's going to be a force from the heat or heats of the water molecule will make the particle go in that direction, and it will feel a drag in the opposite direction. But these two things are going to have exactly the same size. So heat that you get and the Ponce, the opposite direction from the surrounding fluid, will have exactly the same values. This is true when the mass is very small. So this term here. So there is no acceleration. The velocity that you have is determined from the forces that are acting. And in a sense, you can even say that velocity is proportional to force without any acceleration involved. So you apply a force, and as a result, you get a velocity. There is no delay. Okay? If you have mass, there is inertia. There is a. Here now, the microscopic world is biology, particularly. Very small. Yes. Yeah. So you're going to get exactly the Brownian equation now. This guy is 0, and you get x dot gamma cancels with here, and you get what you had. Okay? Yeah. This is already the macro result of the small hits. The macro result has two parts, an average plus fluctuations. Okay, so you have many hits, and these many hits will produce an average result and fluctuations. Fluctuations do not apply micro. The macro result is fluctuating. Okay, so this is, by the way, this equation called Langevin equation. Well, Langevin and Einstein worked on this kind of around this. Okay, this is the Langevin equation. Gamma is going to be important because I'm going to rewrite things a little bit now. So gamma, which is the drag constant, how much energy you dissipate when you are trying to move against a fluid, related to gamma. Now, let me just mention very briefly something called Einstein relation. Yesterday I mentioned that constant of CO2, of ATP, of amino acids had a certain value. Room temperature. Okay, so how do you know how temperature affects fusion constant? How exactly the relation between? So this is called Einstein relation. So one way to derive that is the following. Imagine that you have a fluid, or that you have many Brownian particles in a fluid. The many Brownian particles themselves can be thought also as fluid of interest. You have many Brownian particles we're looking at, but each of them is moving in water. Okay? Anyway, my point is, you have this collection of Brownian particles. You can write, for instance, the pressure that a small volume of these Brownian particles exerts on a surface. So you have many particles. You take a small volume. What's the pressure that this small volume is giving, that the surface of this small volume is receiving from the movement of these? Okay, so you probably remember this equation here. The ideal gas. The pressure is related to the volume and to the temperature, the number of particles inside volume. But I'm going to rewrite things a little bit, the way that physics like. So this is going to be rewritten as this. So C, here's the concentration. It's basically the number of particles divided by volume, which you already have here, except that this is actually moles, not the number of particles. That's why we go from R to KB, which is Boltzmann constant. Doesn't matter. It's a universal number that relate these quantities. Okay. So if you have now a force, an external force that you apply here, say that you try to squeeze, will resist, okay, because of this osmotic pressure, right? Because you have a bunch of particles here diffusing, so they go in the direction of the low concentration, right? Because you are squeezing here, you are increasing the concentration. They will move preferentially in the direction of the low concentration because there is more particles there doing random walk towards the outside than the opposite. I'm going to talk about this. So what we are going to do, I'm going to be brief about this. But you can show that if you have a concentration that is a little bit bigger here, okay, and you try to squeeze this, it will respond force, which is the same size as the force that you are applying. Okay. And how much the pressure changes when you change the radius of this small volume, x, a bit, will be related to the concentration and the force that you apply. In that way. So here you have an equation. Here you have another equation. Let's try to things with. Okay. So you have is the following. We know that we can derive space. So the pressure depends on the radius of the small volume, and therefore I can be written as this. Where C is how much the concentration is changing with del C del X is how much the concentration is changing with. I just realized that I needed a result that I will present afterward. I'm going to use it and then I'm going to. So, concentration particles as a function of x also obeys the following equation. I'm going to prove this later. Okay. 1 over the concentration, del C del X, the force that you are applying, divided by Bragg constant of the particles, times the diffusivity of the particles. Where does this come from? I will show you. This is a gamma, yeah. Okay. Okay. Now, I'm going to join these two pieces of information. I can show that I can rewrite this as a force, and in the end, I'm gonna get the following: 1 over c del c del x equals f divided by kbt. Okay? So basically, I am rewriting this equation. It's not this equation, other one. I'm rewriting this one. I'm not going to give all the details right now. We can discuss this later. I was just checking these results now, because I realized that I was not going to talk about the Einstein relation. This derivation is like one of the first things in the thesis, PhD thesis. Like 2 pages long, very long. So now we have 2 equations for the same thing when we can relate them. When we relate them, we conclude that and this is the Einstein relation. The diffusivity is equal to the thermal energy, kBT, so the constant of Boltzmann's constant times the temperature, divided by the drag. Let's see if this makes sense. To increase temperature, particle will jiggle more, will feel a stronger diffusivity, or undergo stronger diffusion. If gamma higher, it means that the particle receives more drag from the environment and the diffusivity decreases. Okay? Make sense? Okay, so now we can rewrite our Brownian motion equation the following way: x dot equals square root of gamma kBT. Now gamma goes, have 2 kBT of gamma theta. Yeah. So instead of d, you can just say kBT over gamma. Okay? So this is the final version, let's say, at least for now, of the Brownian motion equation. The velocity of the grain, square root of the thermal energy divided by the drag constant, times a Gaussian number. Okay? This is important because we are going to use these to, we are actually going to use these without changing from d kBT over gamma. Okay? But these kind of equation we will use in the hands-on session to simulate a Brownian particle. Okay, now did you realize that I started to talk about concentration as a function of x kind of stuff? I was talking about individual Brownian particles. Now I'm talking about the concentration of many particles. So I'm going to a different kind of approach, a kind of field theory. Like you have a field, concentration field, observable that depends on. You want to describe how this thing evolves in time and depends on position. Okay? So how do we go from random walks? I'm going to go back to easier to talk from random walks rather than from Brownian motion. How do you go from random walks to a field description or concentration description. So to do that, we are going to derive what's called Fick's law. So let me tell you what is. Law says that there is a current of particles in the opposite direction of gradient of constant. So here I have a lot of particles, and here I don't have a lot of particles. Be a current of particles, high to low concentration. Okay? This is Fick's law. But we have to show mathematically exactly what it is. Okay? Otherwise, we won't be. Okay? But do you know why it happens? Why it goes from high to low? What do you need? Puede ser en español. You don't need energy. Only random walks. That's all you need. Something like that. So imagine that you have a lot of particles here. They are all going to random walk. Have only one particle here. Okay? So naturally, there's going to be a lot of particles going there, a lot of particles going there. And only one particle, let's say, going, or even going. So naturally, there's going to be more particles going there than particles going there. Out. So, yeah, that's all you need to explain. But mathematically, how can you derive these? So we are going to do the following. Again, we have discrete space. X plus A. Now I only need these 2 points space. Okay? Okay. So nx, let's say that nx is the number of particles at the x position. You can either say that this is the number of particles at the x position, or between x and x position in this little box. And it won't matter because you're going to do A very small. It's the number of particles around x or in front of x. So now, to define current, just mention the idea of current. To define current, I'm going to put a line here. The particles are crossing the line in this direction, current is positive. If they are crossing the line in the other direction, current is negative. Okay. Okay, so here I can define nx. Here I can define nx plus A. Particles neighboring heights. Okay, so first question. What is the net flux of particles? The x direction. What's the net flux of? After 1 times time. Information that you know is these and this. You know how many we have. You know how many we have. You want to know what's the net flux crossing X in one time step. So how many of these guys will cross to the right? How many? You know that you have n of x. How many n of x will cross to the right? Thinking only of these guys, forget the other ones. How many of n of x will cross to the right? Half of them, exactly. F n of x divided by 2 cross to the right. And you know that out of these guys, half of them will cross to the left. Okay? So the net flux is related to this. How many go right? How many go to the left? It's half of them because the probability to go to the right is the same as the probability. Because we have an unbiased random walk. If the random walk was biased, then you would have a different. And of course, in reality, it could be not exactly half. I don't know, 53% and 47%. There could be fluctuation. But I'm assuming that in each little box, the number of particles is very large. Okay? Each little box. Okay? So 50. Okay, but current is something well defined in physics, which is the number of things that cross an area per unit of time. Okay? So the current, call it Jx, current in the x direction, is actually nx minus nxa divided by 2. Now I have to divide by the area that I am crossing, by the time required to. The area that I am crossing, I'm going to call capital A. Sorry for having two here. So one is capital A, area I am crossing. So you see this line here? Imagine that you are looking like this. There is an area there. Like a tube. 1D, it would be like a tube. Cross section of the area that you are. Okay? And the time of a jump is tau in random walk. What we defined. Okay. Now, what do we do? Now it's simple, because what we're going to do is to rewrite things a little bit, just to get a nicer formula, and then we will make A, the distance, right, go to 0. Then we have our fixed law. But for that, we do not want to work with tau. Because if we are going to make the distance between the sides of the random walk very small, the duration of the jumps will be very small as well. Okay? So we do not want to work with going to 0. But we know that when A, the distance between the sides, and tau go to 0, we can still have that D, the diffusion, finite. D. So to do that, we're going to multiply by A squared here and here. Multiplying by A squared there and there. 1. Okay. But now I can identify following: minus a squared divided by 2 1 over a n x plus a divided by the area minus n of x divided by the area. So there is a minus here because I changed the order here. Okay? And what's this? This is the diffusion coefficient, right? Even though little a and tall will go to 0, no matter these will remain. Okay? Now we have minus d. And what's this? Can you give a name for this? Let's read what this means. This is the number of particles at a site divided by the area of the tube and the distance between two neighboring sites along the tube. So this is a concentration, right? This is a volume. This whole thing is a concentration. I'm going to call it C. Okay, now I'm going to make A very small. Okay? If A is very small, what is this? Derivative. Okay? So you get and in principle, since C can depend on both position and time, I'm going to write the derivative using this line, del, like this, partial derivative. It's the derivative with respect to position. Okay? I mean, to one of the things, in this case, the position. There is only one variable, you do d x for it, but you have x and t, so we do like this. Okay? So, the current of particles is in the opposite direction of the gradient. Okay? This is Fick's law. Okay. Let's move forward. How do we get the diffusion equation now? Now it's the real deal. How do we get the diffusion equation? Because this is not that useful. Because usually what you want is C. You want to know what is the concentration profile. You want to know what is C of x. This is the distribution in space of your biological. Okay? But here you only know that the current is equal to that. You cannot solve this to obtain C. For instance, if you do not know the current from other means, you cannot solve these to find C. That's not that useful. What we really want is an equation that has only C, not C and J. Now we are going to do something called the continuity equation, which is very simple. So let's forget a little bit about a diffusion. Let's assume that, again, at x plus a, this is going to be much faster now. And there is a box here. In this volume, there is a current, J of x, of particles entering the box. And there's going to be a current of particles, J of x, exiting the box. If this current comes from Fick's law or comes from something else, another type of process, not diffusion, doesn't matter. What I'm going to tell you is valid more generally. Okay? Okay, here inside the box you can define concentration C of x of particles inside the box. And the box has volume. Volume of the box is this. A times A. Okay. So in a time tau, okay, tau is not anymore time of the jump in a random walk, but it's the time of the jump in the sense that there are particles moving. Okay? Not necessarily random walk. So the time of the jump is generic process. So in tau, during time tau, you have the following. This amount of particles will enter the box. Okay? Why? Because J, the number of particles per area per time. So if you multiply by area and time, you get the number of particles entering the box. Okay? And what is the number of particles exiting? Have. Realize now that I am using Jx applied at x plus a, right? Because the current here could be different from the current at a different. Okay? Number of particles going from left to right, from the inside to the outside. Okay, so what is the net balance? Net balance is the following. I can now write how much the concentration has changed. Because if the number of particles that went in is different from the number of particles that went out, concentration will change inside the little box. Okay. And it will change in a time tau. Okay? So, concentration at x, which is defined as the concentration in the box. So x here, first one that appears here is just fine. All these x plus a, the concentration behind. Anyway, doesn't matter. Concentration here for time plus tau minus the concentration for difference in the concentration as time goes is how many particles exited is this minus this, right? Or the other way around actually, or that went out. So you get J x. Well, if the concentration increases, then you have enter minus exit. All of these multiplied by a tau. But this was only the number of particles. If you want concentration, you have to divide by the volume of the box. Divide by the. Now you have something very. The tau can go to this left-hand side, and you get 1 over tau C of x e minus C of x, well, in t plus tau in out, equal to minus 1 over a. First the order here. Ax minus ax. So what's this? This is when tau goes to 0. Derivative. Which derivative is this? Let's write it. Nothing. Here you have minus this. Okay? This equation is called continuity equation. This equation is very, 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 very general. Every time that you have a situation where the total number of particles in your system is constant, there are no particles disappearing, no particles appearing out of the blue, you have this. Okay? Because it's a simple manifestation of conservation of particles. Okay? The number of particles that enter the box, they represent an increase. Okay? If you have water flowing down into equilibrium, the current here is equal to the current here. So there is, in between these 2 points, there is no increase of concentration. But if the current here is different from the current here, this has to increase or decrease between the two. This is what this equation is telling us. Now let's put together the continuity equation and Fick's law. So, continuity equation. Fick's law. Fick's law is more specific. Depends on the process. The process, a little bit a stretch to say that diffusion. Things in the universe. But this is more general. Okay? When we put this together, what's the result? The minus cancels. We have this. Second derivative, because you are deriving J, and J is a derivative. You have a second derivative. Okay? And this equation is called the diffusion equation. And it depends only on C, right? You can solve this equation to obtain C, the profile. How the concentration of your biological thing on space and time. Okay? This is very useful. Many papers in biological physics start with this equation or some version of it. Then you solve these either numerically, simulation, kind of simulation, or in analytical. No, because this is not C alone. This is the derivative in time of C, and this is the derivative in space times of C. This is one thing. Not Otherwise, you could cancel del with del as well. This is one thing. Okay? The kind of things that the mathematicians dream about. Okay, so we have our diffusion equation. Now we can try to use it to learn something about this process. Something that is very important is that this equation is deterministic. What does it mean that this equation is deterministic? You see, before we had random walks or Brownian motion, where you needed to draw numbers randomly to do your simulation. Okay? Here you do not have to draw any random number. This is already the result, average result, let's say, of the random process. This evolution here, the evolution of this equation, is completely deterministic. When you do the simulation, you do not need to draw a random number, and the result of this simulation will always be the same. Okay? Because the random things are already taken, it's already the net result, the average result of these random things. Have already the concentration profile of these many jiggling. Okay? And this helps sometimes. What's the solution of this? This is a profile. Okay. The solution is the profile that you want. C of x. Or C of x, t. Okay. So let's plot solution C of x for a certain t. I'm not going to derive the solution. You can do this in many ways. One of the ways is through what's called Fourier. Basically, change C of x to something else, C of a. Then you do things more easily, and then you go back to C. And then you find your solution. But this solution called, it's basically a Gaussian. It's not exactly a Gaussian. The Gaussian divided by square root of time. Square root of time that appears downstairs has to do with the MSD, but it's the result of conservation of probability or of particles in phase. So let's assume that we have a certain initial condition. Every time that you have a differential equation, you need an initial condition. So you assume p of x at t equals 0 had a certain profile. The question is, how does this evolve following? And the initial condition will be this. So if you didn't see this before, might seem very complicated, but all that this is saying is the following. So let's assume that x0 is the initial position of your particles. You're going to have many Brownian particles in the same initial position, x0. Okay? Here's x. This guy here, simplify, is 0 particles. And all of them are x. Okay? So you have a bunch of particles, here's C of x, in the same position. You are inoculating a lot of particles in that. Okay? This is a Dirac delta, which means that the value of this, I already mentioned, the value of this is infinite at x equals x0, and it's 0 everywhere else. Okay? What this is telling us mathematically is that everyone is the concentration is very, very high at x equals 0, and it's 0 elsewhere. Okay? But we have to multiply by n here, where n is the number of particles, the actual number of particles, because you have still a finite number of particles. Okay? And C is the concentration profile of this finite number. When you integrate, when you sum the concentrations across the whole space, you have a certain number of particles, n. The total mass, your collection of particles. Okay? So you have this, the initial, like a peak, the initial condition. And how does this evolve? So the solution, I'm going just to tell you the solution. Xt n divided by 4 pi t time exponential of minus x minus x0, that could not be, for e. Okay, this is the solution. I'm not going to derive this. This is the result. The function that, when you take this function and plug it here, the equation is satisfied. Okay? And how do you see, visualize what this is telling us? So, for a fixed time, t, what you have is a Gaussian. Gaussian appears naturally. And you have the following. I mean, this is already a Gaussian, because this is a Gaussian where the standard deviation goes to 0. Okay? And as time increases, the Gaussian spreads, becomes broader. You have this. Of x, for instance, for a certain time, 1, after the initial, sometime. So it's now broader. Okay? If you wait longer, now it will be like this. Even broader, wider. Okay? But now the peak, lower. Of course, you are conserving the number of particles. You had a lot of them in the middle. Now you have less of them in the middle because they are elsewhere. You wait even longer, you have that. If you wait an infinite amount of time, it will be completely homogeneous. Oh. So this is following fixed. Okay. This is what happens, for instance, when you have perfume in a room. You are inoculating a bunch of particles in a certain position, and they will spread as a Gaussian. And eventually it will become homogeneous. It's a very important kind of reasoning that you can use in many applications, biology, for instance, because proteins and other biomolecules spread out following rules of diffusion. And if you have, for instance, production of a protein or a certain molecule, a certain place, and it will go to another place to do a reaction there, this will follow these. Do you remember yesterday we saw that increase the distance needed to be covered by these particles? the time it takes can increase quite a lot. So the second example that we did, it was 14 hours, like the time required to cover certain. So the distance in these biological processes cannot be that big. Otherwise, it won't. The process won't happen quickly enough. Okay? And things will decay, and you do not have the reactions needed. So things are limited by diffusion. You know, mentioned. They are limited by diffusion, and this sets bounds to the natural biological world. Okay. Okay, now let me do quickly what is called advection. This is pure diffusion. But now, let's say that I have an external force saying you have to go in that direction. Not random, right or left. You have to go in that direction. There will be still the random effect, but there will be combined to it effect to a specific direction. You do this, here you look. Showing anything, sorry, it's port only. When you do this, have what's called diffusion advection process, or diffusion advection equations. Okay? Now it's going to be easier. I think I'm not going to show in details the derivation from random walk, because you already get the gist. So if you have a current of particles, well, first I need to say why. Okay, very briefly, let me just say something. So my overdamped Brownian particle is x dot equals the random force, or the random velocity, because now I'm talking about I'm in the overdamped. Okay, the velocity of the particle is this. Now, let's assume that there is an external force. I don't know, gravity. The particles are so big that they feel gravity. Or the particles are charged, and there is an electric, or there is a flow of water. So there is certain external force in a certain direction. Now, we have this. It would be like this if I was talking about forces. But you remember that I divided the whole equation by gamma to make these velocities, because at force mx 2 dots was 0. So I divided by gamma. In fact, I can call this external force divided by gamma, this is a velocity, I can just call it like an external velocity being imposed. I actually call this drift. The drift velocity. Gamma is gamma is a drag constant. Yeah, I understand what you mean. Not exactly, but there is the opposite part of what you're saying exists. But you're trying to move in a direction and you receive the drag. This is a little bit different to inertia, because inertia gives in at some. It follows. Okay. So you have this. Have a certain drift velocity being imposed. It doesn't mean that the system will have, that the particle will have that velocity, because there is still fluctuations. Thermal force, thermal fluctuations. So it's going to be a combination. Okay. Now, the current that comes from drift can be shown using the random walk, not the random walk because this part is not, but the lattice model with particles jumping sides to sides is get this. Very simple. So the current, the number of particles per area per unit of time going from x to x plus a is the concentration in x times the velocity at which they jump. With which. Okay. But we already had another current which was Fick's law current. The gradient of. So we have to combine the currents. We combine the two currents, we get the following equation. This is only the diffusion equation part. Okay? Now, when we do not know the current, how do we write this? We write only the continuity equation. That's all we know. The conservation of mass statement, which is minus del x of that current. But now we know that the current, the concentration of particles times the velocity being imposed, v drift. So this becomes x v drift. Special derivative, the current, c times v drift. This equation now is called the diffusion advection. So this process of being drifted in a certain specific direction is called advection. You are being advected. Okay, now this is really important because there are many situations which follow the equation. So particles are randomly moving, but they are also being told to go in a certain direction by an external field. One situation like this is electrophoresis. Okay? So let's assume that I'm not going to say that this is a model of a membrane because it's much, but this is an exercise situation. So have a plate with charges here, positive, and here's negative. Okay? This corresponds to some sort, here there is a certain distance, plates, and this corresponds to a certain voltage difference. Okay? Now I'm going to have to appeal to your knowledge on basic charges and electric phenomena, but don't worry about this. I'm going to give the formula. So the difference of charges here creates a field, an electric field. And the difference of voltage is related to that electric field called E and the distance that you play. Okay? In such a way that you have an external force. So here you have particles. Particles are like ions. You have charged particles here. So let's say they are positive. These particles are therefore receiving an external force, which is the charge part of the electron. The electron here. Times the field, which is this divided by this. Okay, now, what is the current, total current, that a particle like this will feel? The particle is in water, giving thermal flux or diffusion, undergoing diffusion. And on top of that, it is being told to go from here to here. Okay? Exactly. Exactly. So the drift velocity is this, as you just said, force divided by gamma. So it's Q E divided by gamma, or Q delta V divided by gamma D. Okay? So the total current is J equals minus D LC del X, the concentration of ions, E, plus Q delta V gamma D, the concentration of ions. This is just the current. I'm not writing the diffusion advection equation. I'm just writing the current, which is Fick's law plus concentration times velocity. Was what we had before. But in equilibrium, let's suppose that we have an equilibrium. This is not actually true in many cases because there's going to be an influx of energy, ATP and stuff, active processes change. Not going to be in equilibrium the way that we are doing here. And let's say that there is some sort of equilibrium where the current is zero. Right? Because if the current does not depend on position, that means that the derivative of J, back to X, is zero, and therefore del C del T, the derivative in time of the concentration, is also zero. Everything is constant. Okay? Doesn't mean that the particles do not move, but it means that the concentration does not move, does not change in space and time. I mean, in space it will follow whatever comes from J being. That's what I'm going to show. So J is equal to zero. There is no net current in equilibrium. Okay? And this will give a relation between these two guys, which will be 1 over C del X equals Q delta V over gamma D, capital D, which is a diffusion constant. If you solve these, you know what is the concentration profile. Why there should be a concentration profile other than homogeneous? Because if there is no charge, homogeneous. But since there is charge, it will be concentrated here. Okay, because it's being told, it's like a sedimentation. If this was gravity, it's like a sedimentation. Dust stays here because there is gravity. Okay? Even though dust is subject to thermal fluctuation. There is a concentration decaying exponentially from this point. Okay? And since I don't have time, all I'm going to say to you is that you assume that concentration here is 10 times smaller than the concentration here. You use real numbers, more or less real numbers here, for an ion at room temperature. you get that delta V 58 MV, which is the order of magnitude of a real voltage difference in a cell. Of course, this is not exactly correct because there is non-equilibrium processes going on. K is not really, but still, you still get the order of magnitude. Thank you. Let's have lunch. Yes.